Hi, everybody. It's Mr. Barbo. Today, we're going to talk about significant figures. And you know what? Significant figures is something that, sometimes will give students some fits. It's a little bit confusing initially, but we will get through it. And you will, with a little bit of effort, understand them. As we proceed and we do labs and we do other calculations, it'll become like second nature for you. Okay. Uh, I want to remind you that the lesson today, all of this information is found on pages 42 through 50 of your textbook. And secondly, either print out this PowerPoint, or I would advise you actually copy any of the notes down. And I have the things written in black text as what I would consider to be the notes that you should have. Some of the examples and things may be in a different color. Don't worry about that. All right, so let's jump right in here. First off, there are two types of numbers. There are what we call exact numbers, and exact numbers are defined numbers or the results of a count. So for example, let me move my head out of there. If we have a dozen eggs, there's no debating that. There's 12 eggs, okay? Same thing, I can count the number of students in a class, and there's no debating that. As long as we can count, we can, we're going to assume that that is accurate. So those are examples of exact numbers. Another type of number then would be measured numbers. And what we're going to find out is when we are measuring things in class, there's always a certain degree of inaccuracy or just inconsistency. And that's because we see things differently. If we're using a triple beam balance or a ruler or a graduated cylinder, I may take a reading and then somebody else will take a reading of the same object or the same volume of liquid and get slightly different measurements simply because of how we're doing that. So measurements then are always going to have a certain degree of inconsistency to them. Now, measured numbers tell us two things. First off, obviously the number that was measured, whether it's 24 centimeters, 3.4 kilograms, whatever, but it's also going to tell us the precision at which that number was measured. All right, not all measuring instruments are the same. We have digital scales that will go to the 10th place, to the 100th place. We even have one that will go to the 10,000th place. And we need to keep that in mind when we're recording our values. So for example, I could measure the same object with two different rulers, and I need to show that. So with one ruler, I would measure it as 34.5 centimeters, but with another one, it would be 34.510 centimeters. And they are the same object, but clearly, this one was measured with the ruler that, for one reason or another, gives us a greater degree of precision. So what are significant figures? Well, there's two things that we need to really think about with this, okay? There are two components, at least as far as I like to teach it. Significant figures are the number of digits in a measurement that contribute to the degree of precision of that measurement. So if I go back just for a second, this measurement has 3 significant figures. This one has 5 significant figures, okay? So that's one component of significant figures, but it also comes into play when we're taking measurements. So whenever we take a measurement, we need to keep in mind that significant figures in a measurement consist of all the digits we know with certainty plus one estimated or uncertain digit. And we'll show you what that means right now. So first off, let's go to the first example. Why do we need significant figures? Well, this comes up all the time when students ask me, well, what should we round to? Well, if we're doing a density problem, for example, and we'll be doing these next week, I'm going to take calculate the density of this cube. All right, so the density is mass divided by volume. And in this case, the mass would be 2.55 grams and the volume is 3.25 cubic centimeters. When I do that math, when I punch those numbers into my calculator, I get this answer. Well, we can't report our answer to this many decimal places. We do not have any instruments in this building that measure to this many decimal places. So it would be wrong to report it that way because we're basically saying, yes, we can measure to this degree of precision, and we can't. So therefore, we would take a look at the numbers that we start with. We always say that, you're only as strong as your weakest link. It's the same thing in measurements. You're only as precise as your least precise measurement. So I would take a look at this, and we're going to get to this in a little bit, but there's 3 sig figs here, 3 sig figs there. That means I should only record my number my final answer to 3 significant figures. Okay, we're going to cover that in just a little bit. Now, the second part of that, here's an example. So we're measuring the same paperclip, okay, but we're using 2 different rulers. And so for this first one, you can see maybe this is just a cheapo free ruler that we've got. And according to our rules, we can report every digit we know plus 1 estimated one. So what that means is I know that this paperclip is at least 2 centimeters. And then this is where the estimation comes in. I would say that's about 0.4. So my answer for this would be about 2.4 centimeters. Now, somebody else might look at that and say, oh, that looks like 2.3, 2.5, whatever. That's where the uncertainty comes in. For the bottom one, however, this is a little bit more precise ruler, where now it goes not only to the whole centimeters, but to the tenths of a centimeter. So I would look at that and say, okay, well, it looks like it's we know it's 2, we know it's 0.123, and I'm just going to estimate that last number as a 5. So we're going to say for this answer, 2.35 centimeters for that paperclip. And you can see how the way we record that answer is going to vary based on the precision of our rulers. Okay, so that's kind of how we would use significant figures in 2 different ways. All right, so here's another one. So we're measuring this nail, and you can see that according to the rules of significant figures, when we take measurements, we know it's 6 centimeters. We know that is 0.1, 0.2, 0.3, and then it's going to be an estimation that looks about halfway between 0.3 and 0.4. So our final answer would be 6.35. That 5 is our estimated number. Okay, we're going to do a lot of labs this year, you guys, where we will we'll put that into practice. Okay, so now what I want you to do is you're going to copy down these rules for deciding which numbers in a measurement are significant or not. All right, you're going to use these quite often. So rule number 1 states that all non-zero digits are significant. What that means is a measurement like this, 1.234 grams, there are no zeros there. Every non-zero digit is significant. Now, the nice thing about these rules, you guys, is you may not completely get the whole concept of significant figures, but you can certainly look at these rules and apply them to numbers to figure out how many significant figures there are. So that's a good first step for us. Second rule, zeros between non-zero digits are significant. So a number like 1,002 kilograms, those zeros, so remember, it really just comes down to the zeros in determining how many significant figures we have. This one has 4 significant figures. All of those numbers are significant. Obviously, the 1 and the 2 are, but since the zeros are sandwiched between a 1 and a 2, that means that they are significant. Okay, rule number 3. Leading zeros to the left of the first non-zero digits are not significant. Such zeros merely indicate the position of the decimal point. So for example, 0.001 degrees Celsius. Those zeros, because there's no number in front of them, these zeros are not significant. So you would only have 1 significant figure. A little bit later in a different lecture, and when I see you in class, we're going to go over the Atlantic Pacific rule for determining significant figures, and it makes it a little bit easier. But for right now, I think it's important to learn these rules. And then rule number 4, trailing zeros that are also to the right of a decimal point in a number are significant. So I apologize for having this thing down here. Let's get that out of here. So in this case then, 0.0230 milliliters has 3 significant figures. Those first 2 zeros are not significant, but that last one is, because again, it's telling you the degree of precision in that measurement. Okay. Now this one for number 5, when a number ends in zeros, there are a couple of different possibilities. It all depends. Well, there's a couple ways to handle this. Let me move me out of here. If the number ends in a decimal point, the zeros are significant. So let's say we have 3,200 meters, kilograms, whatever. If I put a decimal point there, that indicates that these zeros are significant. So that means we would have 4 significant figures. If I have 2,300,000 and there's a decimal point there, those numbers, those zeros are all significant, and I would have 7 significant figures. If the number does not end in a decimal point, the zeros are not significant. So this one, there's no decimal point here. So there's 2 sig figs, and then this one, again, no decimal point, 2 significant figures. So we may have a pretty large number, but the fact is there's only 2 significant figures there. Now, one way we can avoid this ambiguity or confusion is we can use scientific notation. So when we write a number in scientific notation, don't worry about the exponent. That does not indicate the number of sig figs. Instead, the coefficient does. So for example, depending on whether the number of significant figures is 3, 4, or 5, we would write 50,600 calories as 5.06 times 10 to the 4th, which means we have 3 significant figures, 5.060 times 10 to the 4th, which gives us 4 significant figures, or 5.0600 times 10 to the 4th, which gives us 5 significant figures. So you can see however many numbers there are here, those are the number of significant figures. All right, so that makes it a little bit easier when we're dealing with zeros. So what I want you to do is take a few moments in your notes and pause the video, copy down these numbers, and write down the number of significant figures in each of them. All right, so go ahead and pause it now, and when you're ready, hit play again. Okay, so hopefully you got those numbers down. So let's see how we did here. 28.6 grams. There's no zeros there, so therefore we have 3 significant figures. 3,440 centimeters. There's a decimal point there. That means the 0 is significant, so you should have 4 significant figures. 910 meters. That 0, because there's no decimal point, is not significant, so you have 2. 0.04604 liters. These leading zeros are not significant, but that one is. So 1, 2, 3, 4 significant figures. Okay, for this one, these leading zeros are not significant, but those trailing zeros are. They indicate a degree of precision. So we're going to have 1, 2, 3, 4, 5 sig figs. Scientific notation, we will have 3 significant figures because there's 3 numbers there. And for 60.004 milligrams, there are 5 significant figures. All right, let's try some more. So go again, pause the video, answer these, and then we'll put the answers up in just a second. Okay, so for the first one, you have 3 significant figures, 5 sig figs, 2 significant figures. Those leading zeros are not significant. 4 significant figures, 4 significant figures, 3, 2, and 5. Okay, hopefully you did pretty well on those. If you didn't, you guys, go back and look at the rules. All right, you can figure this out. All right, I have faith that you can do that, but look at the rules and apply them to these numbers. All right, now, what do we do when we are doing calculations? All right. So there are a couple of different rules when we're doing calculations using significant figures. So in a lab, when you're doing math and you're using measurements, how do we do this? Well, when you're adding or subtracting, they all follow the same type of rule. When adding or subtracting decimals, the answer must have the same number of digits to the right of the decimal point as there are in the measurement having the fewest digits to the right of the decimal point. So here's what this means, you guys. If we take 2 numbers that we're adding or subtracting and we line them up so that their decimal points are even, and you don't have to do this, it's just for to make it a little bit easier for you to see. This number goes 2 places past the decimal point. This one goes 4 places past. No matter what we do, when I add those together, yes, I can calculate it to be 8.0503, but I can't express my answer like that. I can only go as far as the one, as this one, so to the hundredths place. So my final answer then would be 8.05. I just dropped the other numbers. All right, so when we add and subtract, it all depends on how far past the decimal point do you go with any of the numbers that you're adding. Okay, you cannot be more precise than the least precise number. Now, when we are multiplying or dividing, it's a little bit different. Now it comes down to how many significant figures are there in the numbers that you're multiplying or dividing. Okay, so in this case, we have 2.4 meters, excuse me, times 15.2 meters. If we calculate this, it comes out to be 36.48 square meters. Well, here's the problem. This number only has two significant figures. This one has three, but we have four significant figures in our final answer. We can't have that. So again, for this one, we're going to look at whichever number has the fewest significant figures. In this case, it's 2. So we're going to drop, let's see, whoops. That should be, I goofed up. That's going to be 37. So I will fix that on the PowerPoint. But since this has 2 and that has 3, we should have 2 significant figures. So I will change that to 37 meters squared. Okay, 37 is the correct answer for that. Sorry about that, guys. So let's try a couple practice problems. Go ahead and pause the video, write these problems down, and we will go over the answers. Okay, first one is an addition problem. We go to hundredths place, but we don't even go past the decimal point here. So therefore, our final answer cannot go past the decimal point. So whatever you calculated, stop it at the decimal point and drop those final numbers. Second one is a subtraction problem. Same thing. This goes 3 places, this goes 2. Our final answer can only go 2 places past the decimal point. And then finally, we have a multiplication problem. 3 sig figs, 2 sig figs. Our answer can only have 2 sig figs, so 11 meters squared. Now, last thing that we need to cover before we're done is when we have to drop numbers, how do we round? Okay, so in correcting a number, if we're going to express that proper number, express that measurement to the proper number of significant figures, we have to drop unwanted digits. That's what we've done, okay? So the rules for rounding off: if the digit immediately to the right of the last significant figure is more than 5, you round up. Actually, I take that back. If it's 5 or up, you're going to round up. If the digit immediately to the right of the last significant figure is less than 5, you round down. Now, here's the thing. There is an entire other set of rules that deals with rounding when that number is a 5. We're not going to get to it right now, okay? So right now, 5 or more, we round up. Less than 5, we round down. When we have time in class, I will show that to you, but that's almost an entire different lecture on rounding. All right, so in this case, if we have a number 35.76 and we need to record that to 3 significant figures, here's the last one we're keeping. We look at the 6, it's 5 or more, so it becomes 35.8. 35.74 is going to be 35.7. You've done rounding before, so that's basically the same idea. All right, what I want you to do now is pause the video and copy down all of these numbers and round them to the correct number of significant figures. Okay, so pause it and I'll put the answers up in just a second. Okay, so hopefully you got those done. So let's go over the answers, you guys. 72.49 to 3 significant figures is 72.5. Okay, 299,000 to 1 significant figure. We have to keep this last one is 300,000. Now, a common mistake is sometimes students will drop all the other numbers and just put 3. Well, that's not the same. That doesn't go to the same place value. If I owed you $299,000 and I gave you $3, you're going to be upset about that. So we have to just replace all the numbers with zeros. 45.52 to 3 significant figures is 45.5. 92,528 to 4 significant figures is 92,530. Okay, 120.05 to 4 significant numbers becomes 120.1. 13,052 to 3 significant figures is 13,100. 239.5 to 3 significant figures is 240. Now notice I put the decimal point there. That makes that 0 significant. I could have also put 2.40 times 10 to the second. Okay, 2.448 times 10 to the fourth to three significant figures is 2.45 times 10 to the fourth. 28.149 to three sig figs is 28.1. 32,000 to three significant figures is 3.20 times 10 to the fourth. 63,500 to two significant figures is 64,000, and 82,919 to three significant figures is 82,900. Okay. So here's what I want you to do. I am going to post an assignment today from your textbook that will ask you to identify significant figures and do some calculations and some rounding to test what we're doing. Again, all this information is in your book, you guys. Please refer to the examples that are given. There will also be worksheets. If you were in school on Monday and Tuesday, you got your worksheets. Those are due on Monday. If you are coming to school on Thursday and Friday, I'll give them to you when I see you. Those are also going to be due on Monday. And if you're at home, what I'll do is I will scan those and post them so that you will be doing those at home. Okay. This is going to be a little confusing for you initially, guys. Just power through it, use the examples from the book, and I'm confident that we're going to be successful with them. If you have any questions, send me an email. Have a wonderful day, and we'll see everybody soon. Bye-bye.